Greetings. So here's some help for you. This problem. So first thing we'll look at, you see a standing wave. This is the thing I want you to recognize. How big is one wavelength? So when I see this, I gotta ask myself, how many wavelengths do I have? Well, I have, let's see, this section, every section is half a wavelength. So that means this is half a wavelength, and this is half a wavelength. Or another way of looking at it is I have 1.5 or 3 halves wavelengths. Okay. Tension to string, the mass per unit length. All that means, the reason I have to say that stays the same is that affects the speed of the wave. And they're saying that doesn't change. So speed is always the same from one situation to the next. It's not a big deal. It's just a detail they have to give us. All right. Which of the following frequencies could not also produce a standing wave? Okay. So let's go back. For that same string, let me see here. So for that same length of string from there to there, what is the most fundamental frequency or shape of the standing wave? And that would be a standing wave that would have one section. And that would be half a wavelength, but more importantly, that would be the fundamental frequency. What would we have to do to get the next, what they call harmonic, the next standing wave? Well, you'd have 2 sections, and so that would be 2 times the fundamental frequency. Wait a second. That must mean that this represents 3 times that fundamental frequency. But they tell us that that's 60 hertz. That means in order to get a new section, you have to increase the frequency by 20 hertz, because that must be the fundamental frequency. So this, for example, the frequency would be 20 hertz. This would be 40 hertz. This is 60 hertz. If you wanted one with 4 sections, it would be 80 hertz. So which of these, basically what it comes down to, is not a multiple of 20? And it's that guy. All right, you're not gonna, if you put 30 hertz, you're not going to get a standing wave. Next, Doppler effect. We didn't discuss Doppler effect much in class, so not surprised you got a question on it. So here's the deal. If an object is stationary and it emits a crest, and then as sometime later it emits another crest, those crests are going to move out in all directions at the same speed. But what if the object itself is moving? Well, what that means is that the crest that it emitted when it was, say, back here has now gotten bigger and is, like, say, like this, but it's still centered around when it was back here. And now it's here. And so what happens is the one that it emitted, say, here is now like that, and the one that it's emitting right now is like that, and what happens is if it's moving that way, the crests get piled up in front of it because it's chasing after its crests. And at the same time, in the opposite direction, it's leaving its crests behind. So this is definitely an object moving, in our case, to the right. So a small vibrating object, S, moves across the surface of a ripple tank, producing the wavefronts shown above. The wavefronts move with the speed v. Okay, so in what direction and with what speed relative to the speed of the wavefronts is it moving? Well, it's definitely moving to the right. Check. All right. So if an object is moving as fast as the waves it produces, you end up with this situation. A situation, assume those are circles, where all the waves are piled up in one strong front right in the front of them. So it would look like they'd all just be crammed completely together there. In fact, that's why they had trouble breaking the sound barrier, because of that wall of high pressure air in front of the plane. So that would be what's called a bow wave. If an object's moving faster than the speed of the waves, then the object might be here, and the wave it produced a second ago is going to be back here. It's going to be past it. And the one it produced before that is like here. And the one before that is here. And the one before that is here. And it will look like this. And you actually get a high pressure cone called a shock wave. So when something's going faster than the speed of sound, you hear a sonic boom. That's the shock wave from that. So this is faster than the waves. This is as fast. This is moving, but not as fast. So we're going to say it's going to the right, but less than v.
Figure above, I haven't read this problem yet. Figure above represents two guitar strings on different materials and lengths of different, which are on two guitars of different sizes, hence the different lengths, I guess. String 1 is plucked so it vibrates in the pattern shown above. Very soon after string 1 is plucked, string 2, which is a short distance away, vibrates in the pattern shown. The guitars are placed in a sealed chamber, and the air is then pumped out of the chamber. Who comes up with this stuff? String 1 is again plucked and vibrates in the pattern shown. Does string 2 vibrate in the pattern shown, and why not? And the answer would be no. Because without air to conduct the sound, there's no physical means for this string to affect the other one. The same way you wouldn't, when the Death Star explodes in Star Wars, you wouldn't hear a thing, because there's no air in space. So, no. Not because no, because almost no energy is going to reach it, because there is no medium to conduct that energy over. So I would go with D as my answer. All right, this one. Okay, what we want to know from this
Is the following. So in a pipe, just real quickly, if a pipe is open at both ends, and I realize that's not what we have here. Anytime a pipe is open, the end of a standing wave is actually going to be a antinode, a high place of high amplitude. In fact, the most basic wave you can have in a pipe that's open at both ends, the most basic standing wave, is this one, which is actually a quarter of a wavelength plus another quarter of a wavelength. So it's actually half a wavelength, which is what it is for a normal standing wave on a string. It just looks a little different. However, if a pipe is closed at one end and open at the other, closed ends, the end of a standing wave will always be a node. And so, in this case, the most basic wave we can have is this one. That's the fundamental, and it's actually only a quarter of a wavelength. The next harmonic, the next standing wave you're going to get out of that same pipe, so let's make it the same length, is actually going to be one that looks like this. So it's going to be a quarter of a, well, it's going to be a half a wavelength, and then a quarter, like so. So the next one is going to be 3/4 of a wavelength, and so on and so forth. So the figure above represents a standing wave patterns in two identical tubes. So the tubes are identical. This distance here to here is identical in both of them, if I read the question correct. Standing waves are produced by, okay. What is the relationship between the wavelengths x? So, first of all, this is one complete wavelength in x. And that is certainly smaller than the wavelength here, because this is only a quarter of a wavelength. And if that's a quarter of a wavelength, that means, just real quickly trying to draw, if that's a quarter, well, that's a half, and that's a full wave. So the wavelength is actually about that long, attempted. So certainly the wavelength in x is going to be less than the wavelength in y. So, is there any of these that I can rule out? x has got to be less. That means x, so y times some fraction is going to be x. So I think I can rule out this, because y is already bigger, and you're going to multiply it by 7. There's no way you're going to make equal to x. And we can therefore rule out this as well. Gone. All right, so the question is, are we talking 1/7 or 2/7? Let's figure this out. Let's see. Well, this right here is L, and this is L. Same length. So on the left-hand one, x, L is equal to, let's see, 1 3/4 wavelengths. Is that right? There's a half, another half, 3, and so that's going to be 1 3/4. That's going to be 4. That's going to be 7/4. So 7/4 times wavelength of x. Let's make sure we get that right. All right, 7/4. Yeah, almost 2 times the wavelength of x. Right here is the wavelength of x. Whereas the L on the other one is equal to 1/4 of the wavelength of y. This represents only 1/4 of a wave. But those two lengths are equal. So 7/4 wavelengths x equals 1/4 wavelength y. And if I take that and I solve it for x, because that's what they have by itself over here, let's say I'm going to multiply both sides by 4/7. So I'm going to go x equals 4/7 times 1/4 wavelength y. 4 is going to go, so I have 1/7. Wavelength x equals 1/7 wavelength y. So recognize this as 1/4 of a wavelength. Right? That's this part of a wavelength. And a wavelength, let's see, that's 1/4. This is the other quarter. Remember, this section's half, and then there's the whole thing.
Hopefully, this helped. Now get some sleep.